Swayam Prabha, free DTH channel for education.
Greetings. In our previous lecture, we talked about what teleportation is not. Today, we will discuss what it is, how is it achieved, does it violate the limits of information communication set by the speed of light. And these are some of the questions that we will tackle today. Certainly, entanglement is there, and that is a law of nature. Laws of nature happen to be quantum mechanical, not classical. And this huge debate between Bohr and Einstein was to a fair extent settled by Bell's inequalities. And it sort of explained to us that what kind of correlation, statistical correlation, can exist when laws of nature are governed by quantum laws and not classical, because the classical correlation function is different from the quantum correlation function. And every experiment has borne out the fact that the quantum entanglement is there, in which is best accounted by the laws of quantum mechanics. So let us see if quantum entanglement enables us to communicate information. And the question in front of us is that Alice has got a certain quantum of information, and it is there in a certain qubit. This is the qubit which Alice has. It is a point on the block sphere. It is a superposition of 0 and 1. It is an arbitrary superposition. We do not know the values of A0 and A1. So we do not know where the point is on the block sphere. It is somewhere on the block sphere. This is an arbitrary state. And this quantum of information is what Alice would want to be communicated to Bob, who is at a remote location. But there is a certain resource which is available to them. And using that resource, they can possibly achieve it. And we are going to figure out how this would happen. So this is the quantum of information to be communicated to Bob. This is a qubit. It's a superposition of 0 and 1, like a cat being in a state of being dead and being alive. But Bob and Alice have two other qubits also. And we will see how those qubits are used to communicate this information, which is a superposition that I will refer to as the state chi. So it is the state chi which is to be communicated by Alice to Bob at a remote location. And they're going to use entangled qubits. They will use Bell states. And between two qubits, you can have 4 Bell states, which we have discussed earlier. And what extra resource they have between them is 2 other qubits. It's not this qubit, which is the state chi, which is to be communicated. In addition to this, this is qubit number 1. There are 2 other qubits, and these are qubit number 2 and qubit number 3. And qubit number 2 and qubit number 3 are correlated in a Bell entangled state. This state cannot be factored as a product of individual vectors. So this is the Bell state of qubit number 2 and qubit number 3. And just for the sake of discussion, we consider that the initial Bell state which Bob and Alice have is this. Now, it could be any one of these four, but just for the sake of discussion, I have chosen the qubit to be this, in which the spin, if your model qubit is a spin half particle, which is always a very nice system to work with. It's prototype of all other qubits because they follow similar logic, which is the quantum logic, not the Boolean algebra, but the quantum logic. So in this, if Alice has up, then Bob has down. And if Alice has down, then Bob has up. And these two states are in a superposition state with a minus sign. The probability that Alice has either 0 or 1, either 0 or this 1, is half. It's random. It could be either 0 or 1. And those two probabilities are both 0.5. So they are equal to each other. It's therefore random. However, what is guaranteed is that if Alice has up, then Bob will definitely have down. And if Alice has down, Bob will definitely have up. And that is guaranteed because one particle, particle number 2 and particle number 3, the qubit number 2 and qubit number 3 are in a state of entanglement. They are in a Bell state. So this is the initial resource which is available to Alice and Bob. And now with this initial condition, you have to be careful with this because you are not going to tamper with this at all. If you tamper with this, it will no longer stay in this superposition state. And it is this superposition state which is to be communicated to Bob. Any measurement will induce the system to collapse into an eigenstate. This is the initial resource. And now what Bob does is that he takes qubit number 3. It is a different physical system. It is entangled with qubit number 2, but it is in a state of entanglement. It is correlated. Its vector cannot be factored out. Nonetheless, it is an independent physical system. And Bob carries it with him to a remote location. So Bob goes away with qubit number 3. It remains entangled with qubit number 2, which is with Alice. And Alice, of course, is in possession of qubit number 1, which is in the state of superposition, which is the information which she intends to communicate. So we have this initial condition. Bob has now moved away. And where has he gone? He could go to the next room or to another country or to another galaxy, wherever. The distance between the two qubits is of no relevance at all, because as long as anything is done to the qubit, it remains in that state of superposition. It remains entangled, and qubit number 2 and qubit number 3 remain entangled no matter what is the distance between Alice and Bob. So Bob is at a remote location and Alice is in possession of the original qubit 1, which is the challenge qubit, which is the information to be communicated. But she also has with her qubit number 2, which is entangled with qubit number 3, which Bob has taken away to a remote location. And this is the Bell state in which qubit number 2 and 3 are entangled. So 2 and 3 are entangled, and they remain entangled as long as anything is done to either. And now what Alice would do is to entangle qubit 2 with qubit 1. So she now does an experiment. She has got a very sophisticated laboratory, and she entangles qubit 2 with qubit 1. So this is the correlation which is now built. And as a result of it, because 2 is entangled with 3, the state of qubit 3 is impacted in a unique manner. that is due to the correlation between qubit 2 and qubit 3. So Alice would now entangle qubit 2 with qubit 1, but Alice can do it in different ways, because between qubit 1 and qubit 2, as a result of the entanglement, she's going to form a Bell state, but there are 4 different Bell states. And which of these 4 is she entangling qubit 1 and qubit 2? Now that's something which Alice knows and Bob doesn't, unless Alice informs him. So we'll come to that part of the story a little later, but just keep it in mind that Alice can entangle qubit 1 and qubit 2 in a Bell state, but it can be one of the 4 Bell states, and Bob doesn't know which Bell state, which of these 4 Bell states has Alice entangled 1 and 2. And he would need that information to process his qubit 3 to get further information about the original challenge qubit, which is qubit number 1. So what is Alice going to do? So let us first of all construct the 3 qubit vector, of which qubit 2 and qubit 3 are in a Bell state. This is the initial Bell state that we have considered. This is the vector. This is the superposition state point on the Bloch sphere whose quantum information is to be communicated to Bob. So you have 3 qubits, of which 2 and 3 are initially entangled. So this Bell state cannot be factored further as a product, as a tensor product of qubit 2 and qubit 3. This is an entangled Bell state. This one is the 3rd qubit, and this is the 3 qubit vector. The 3 qubit state is now a product of this 1 qubit and this 2 qubit Bell state. So let us work out this product, and you have to do it term by term. So you have A0 here, then this multiplies this vector, which is 0, 1. It is here. Then you have this vector with the coefficient A1, which comes here. And then you have this vector, which multiplies this vector. And you have 2 vectors over here and another 2 over here. These are 2 qubit vectors. And you get a total of 4 terms over here. You just multiply it out. There is nothing beyond it. But do it carefully, because there is a minus sign here. That is because of the particular Bell state in which qubit 2 and qubit 3 were initially entangled. So keep track of that sign, which is why you have a minus sign here and a minus sign here. And let us write out this product a little bit neatly. So there are 3 qubits, qubit 1, qubit 2, and qubit 3. It has got 4 terms, the first of which is with Alice. The second qubit is also with Alice. It is the 3rd qubit, which is with Bob. So look at the indices. Qubit 1 is with Alice. Qubit 2 is also with Alice. Qubit 3 is with Bob. And same over here. Qubit 1 with Alice, qubit 2 with Alice, and qubit 3 with Bob. Because Bob has moved away, he has gone away somewhere in some other galaxy, some other part of the universe with qubit number 3. So this is the 3 qubit vector, of which 2 and 3 are entangled at this point. Alice has got qubit 1 and 2, and she can do experiments with 1 and 2. She's in possession of qubit 1 and qubit 2. Qubit 3 is not in her possession. And she can do experiments with qubit 1 and qubit 2, and she entangles qubit 1 and qubit 2. But there are 4 different ways of entangling qubit 1 and qubit 2. So what Alice does is to entangle qubit 1 and qubit 2. The initial condition was it is 2 and 3 which were entangled. But now Alice entangles 1 and 2, and she can entangle 1 and 2 in one of these 4 Bell states, which we have discussed earlier. These are the 4 Bell states in which both the spins are up or both are down, but one combination is with a plus sign and one with a minus sign. In this case, one is up and the other is down, but the combinations can have either a plus sign between them or a minus sign between them. So that's what gives us the 4 entangled Bell states. And Alice would entangle qubit 1 and qubit 2 in any of the 4 states. And let us presume, for the sake of discussion, that it would entangle qubit 1 and qubit 2 in the Bell state number 4, which is really this. So you have got 4 Bell states denoted by beta for Bell, and the subscripts are pi over here, pi for parallel, in which these 2 vectors, the spins are parallel. These are also parallel. So there are 2 parallel ones, one with a plus sign and the other with a minus sign, or they can be anti-parallel, 0, 1 and 1, 0. These are anti-parallel combinations. So these are the 2 alphas, the anti-parallel combinations, one with a plus sign and the other with a minus sign. So these are the 4 Bell states. And let us say Alice is going to couple qubit 1 and qubit 2 in a state of entanglement, which is the Bell state number 4, which is this beta alpha minus, which is the 0, 1 minus 1, 0. So that is the Bell state in which Alice would entangle particle 1 and 2. She could have done it in any one of the 4, and whichever Bell state she chooses to combine to entangle qubit 1 and qubit 2, the probability amplitude that the 3 qubit vector will be in the jth Bell state, where j is either 1 or 2 or 3 or 4, is given by this inner product. This is the projection of the 3 qubit vector on the Bell state, which is the jth Bell state. And this will give you a measure of the probability amplitude that the 3 qubit vector has got a component in that particular Bell state. The corresponding modulus square of that probability amplitude would give you the probability. So this is the usual Born approximation, Born interpretation of probability. So you have this 3 qubit vector, and Alice entangles qubit 1 and qubit 2 in Bell state number 4. We have just discussed what this particular Bell state 4 is. It is this combination in which the 2 spins are oppositely oriented. One is up, the other is down, and there is a minus sign over here. So this is the particular Bell state which we have considered here just for the sake of discussion. And of course, she could have chosen some other Bell state, and we will discuss one of those examples as well a little bit later. So our first example is the one in which the Bell state in which she entangles qubit 1 and qubit 2 is this 4th one, which is 0, 1 and 1, 0 with a minus sign between them. And you can see that it is these 2 terms which will give you a non-zero component. These 2 terms will give you a non-zero component along this Bell state number 4. There are 4 terms, okay? This has 0, 1, and this has 1, 0. So these are both are present in the Bell state number 4, but this is 0, 0, both are parallel, and this is 1, 1. Here also they are both parallel. So they belong to the Bell state number 1 and 2 rather than Bell state number 4. So these 2 terms will give you a 0 probability amplitude, whereas these 2 will give you non-zero terms. So let us estimate this probability amplitude. So to do that, let us determine this probability amplitude that the 3 vector has a component along Bell state number 4, and this is the Bell state number 4. Yes, there is this normalization 1 over root 2 and so on. We'll take care of that at the end. So we will not worry about the normalization at this point. There are, of course, also these factors A0 and A1, which A0 is here and A1 is here. So we will take care of those factors a little bit later. Okay, so let us determine this probability amplitude. So these are the two terms which are of significance. Mind you, there is a minus sign in Bell state number 4, which is why you have got a minus sign over here. So this is of significance and importance. You must take care of that. And here it is. So this is one term which will give you a non-zero projection, because this is 0, 1. And sure enough, it has got a component along here. And this probability amplitude will, of course, be scaled by A0, right? But with a minus sign, and there is an implicit plus sign over here. So this probability amplitude will be scaled by a minus A0 term. And notice that corresponding to this, the qubit 3, which is with Bob, who is at a remote location, is in the state 0. So that's something to keep track of. So this projection is minus A0, and the other projection will come from this term. The first term is contributing minus A0, corresponding to qubit number 3 with Bob is in the state 0. And let us look at the next term, which is coming from here. This is 1, 0, and sure enough, it has got a component in Bell state number 4, which has got 1, 0 over here. But mind you, there is a minus sign here, a plus sign here. So this probability amplitude will be scaled by a factor of A1, but it will pick up a minus sign from here. So there is a minus A1 to keep track of. And corresponding to this probability, the qubit number 3, which is with Bob, is in the state 1. So I think we have compiled a lot of information now. This is the qubit number 3, which is in the state 1 for this combination. And let us now compile all this information. This projection, the probability amplitude, this 3 qubit vector has got a component along Bell state number 4 is minus A0 with qubit 3 in the state up corresponding to 0, and probability amplitude A1 also with a minus sign with qubit 3, which is with Bob, in the state down, which is the state 1. So that is our notation. Now, both of these have a minus sign. So we can take it, factor it out as a common sign. We can always absorb it in the overall normalization. So we will not worry about this minus sign anymore, but only because both of the signs are minus. If one of them was minus and the other was plus, then of course we could not have done that. So we take this particular combination, we find that Bob now has his qubit 3 is in a state which is a superposition of 0 and 1 with weight factors with coefficients A0 for spin up and A1 for spin down. So this is the vector that Bob has. Bob has qubit number 3. It is represented by a point on the block sphere. This is the block sphere number 3 for the third qubit. And what is this vector? It's just the vector that Alice wanted to communicate to Bob. There is a factor of half, which simply comes from the fact that there are 4 Bell states, so each would contribute 1/4, so that can be taken care of. So that's not particularly significant. But this is the state which describes the qubit number 3, which is in possession of Bob. And this is just the qubit number 1, which we originally started with, which was the information. This is a superposition of 0 and 1. 0 is scaled by A0, which is what it was in the original qubit. And 1 is scaled by A1, which is just what was scaling the state 1 in the original qubit number 1, which is the quantum of information that Alice wanted to communicate to Bob. So Bob already has his qubit number 3 in exactly the same quantum superposition state which Alice wanted to communicate to him, except that Bob doesn't know that he has it. How would he know that? Because Alice could have entangled qubit number 1 and qubit number 2 in any which way. So this happens to be the case because Alice chose to entangle qubit number 1 and qubit number 2 in the Bell state number 4. She could have entangled 1 and 2 in some other Bell state. And then Bob would not know what is the state of his qubit. So now Alice is going to have to tell Bob. And how is she going to tell that? She can send a messenger. She can send a letter. She can send an email. She can make a phone call. Or she can use a laser flashlight and have some sort of code that, okay, if I have 2 pulses, it is the letter A. If it is 3 pulses, it is the letter C or whatever. They can have some sign language between them. And that information, whether it is a messenger who is carrying this information all the way from Alice to Bob, or a letter, or an email, or a laser flash signal, whatever that medium is which is used to communicate this information, that Alice is informing Bob that she has entangled qubit 1 and qubit 2 in Bell state number 4. That is information which is to be communicated. Once Bob gets that information, he can conclude that the state of qubit 3, which he has, is already in the same superposition state. He doesn't know the value of A0 and A1, and Alice did not know it at the very beginning. Because if any experiment is done on qubit 1 or qubit 2 or 3, any qubit, then the system collapses into an idle state. So the values of A0 and A1 are not important over here. It is the superposition which is important. And the same superposition that Alice had to begin with in qubit number 1 is now with Bob. And Bob concludes that he has that superposition after Alice sends a message or flashes laser light. And that is a classical channel. It will go according to the fact that no information can be communicated at a speed faster than the speed of light. So the limits of the special theory of relativity are not being violated in this entanglement. Entanglement is not just instantaneous, it is always there. And I like to make a distinction between communication, which is instant communication, and communication that is always there. Because even if it is an instant communication, you get a feeling as if the information is originates at one point and then transported to another point. That's not entanglement. Entanglement is always there. That information is always there between the entangled species. Whether the two entangled species are here or there or galaxies away from each other. It doesn't matter how far they are. Throughout this process, the entanglement always survives as long as there is any interference with the qubit. So without violating the limits that we are familiar with from the special theory of relativity, Bob certainly gets that information. But mind you, this is not cloning. Bob has the same superposition as Alice had, but not the same information that Alice now has, because Alice's qubit number 1 has undergone a transformation. It has got entangled with qubit number 2, so it is no longer in the state that this one was. So the original superposition is destroyed. It is destroyed at Alice's end, but that information has gone intact, exploiting entanglement to Bob, who is at a remote location. Okay, so this is not cloning, this is not copying, because in a copying machine, you insert an original, you insert a blank sheet, blank piece of paper, and what comes out of the copying machine is the original and a copy of the original. Here, the original is no longer in the same state as it originally was. It has got entangled with qubit number 2. So this is not cloning. You already know this because in our earlier class, we have discussed the no cloning theorem. It has got a very simple proof, which we have already discussed. And here is a mechanism which enables teleportation of quantum information from Alice to Bob, who is located at a remote place. But of course, Alice has to inform Bob that she has entangled qubit 1 and qubit 2 in which particular Bell state. So only after the communication of this information, for which classical channel is used, can Bob get this information. So the original is not, it does not continue to survive. There is no cloning. The limits of special theory of relativity are not compromised, but the quantum of information which was there in the original superposition has definitely been sent away to a remote location. So thank you all very much and goodbye for now.